Alright, video kind of specifically on one subject, making a simulation of the double slit experiment that illustrates the real mechanics versus the wave mechanics. So fundamentally it's difficult because you can't visually see something of some kind of comparable circumstance, okay, in terms of sizes. The sizes are all wrong, so to visualize it, you have to abstract certain parts of it. It's like if I was to blow sand between two houses or something, call that a double slit or whatever, a single slit. The little tiny sand particles are so small, and this is all dependent on aspects that we can't see, such as frequency, little tiny nanometer differences between distances. So you have to build that into the simulation. You have to show one thing and you have to mathematically do something different, I suppose, because you really can't do both. You can't show a 1 millimeter slit and then a 7 meter screen in the same image. That's not going to work. So your simulation starts with like this burst of yellow or red. It turns yellow, and I don't know what that means exactly. And then you burst another burst, and it's already violating all the fundamental rules I tried to establish. And so you'd say, okay, you're already starting with the wrong premise. So, well, we use the double slit, just because that's what you're doing. As stated, you have to recognize that 500 nanometers is an important fact. The wavelength is important, so it has to be in the simulation. These distances have to be in the simulation. With this distance and this distance have to be understood as critical to the function. And then the distance to the screen is another distance that's critical. So that's it. You have to have those components have to be in, and you have to understand what exactly is happening when the photons go through. So the first point to make is 90% of the photons aren't bothered. Okay, so they go right through, and that ends up creating a bulge in the envelope pattern. But regardless, it doesn't really matter. The only photons that matter are the ones going by the surface. So that's the first thing to understand, is the photons, most of them go straight through unmolested, undisturbed. But they're only a millimeter apart, so to speak, so there's always going to be some kind of brightness in this area. Brighter. In the double slit, it's not as bright as in the single slit, but for the sake of this argument, it doesn't really matter. Anyway. Alright, so the next part of it is you got this little source. So you have to represent the frequency. And as I've said, the photon isn't just one thing. It's a series of things. It's an event that takes place. To see a photon on a surface, there has to be a hit, a hit, a hit, and a hit, let's say. 4. Let's say you have to have a minimum of 4 little bits of energy hit the surface, or there's not going to be something called a visible photon. So the photon is made out of bullets, and the pattern, you can't see any of that. Very good. It's a pattern. Okay, it has to have this. This is the 500 nanometers. In between them, 500 nanometers, 500 nanometers. Okay, that's the distance between the little bits, and 4 of these have to hit a surface or there's no photon. It's no photon unless 4 hit, and the 4, I'm just using 4 as an arbitrary number, have to be with the 500 nanometers of distance between them, the amount of time that 500 nanometers at the speed of light equals. Okay, and I can't remember that off the top of my head, but it is a certain amount of time, okay, that these are separated by. And that's a photon. So that's what's coming out of the gun. What's coming out of the gun is a continuous bunch of elements exactly the same distance apart. So it's not a blob. It's not a bunch of stuff compressed into an area. It's a distinct frequency between them, a distinct difference between their distances that they're going in. Okay, and they're going in continuous. So you just have a bunch of sand, okay, little grains of sand, and the little grains of sand all have the same separation between them. Okay, so if you were to draw it, if you would try to zoom in on it, that's sort of what it would look like, is a stream, you know, a blob of, you know, here's a bunch of them, then there's none of them, then there's a bunch of them, and then there's none of them, and then there's a bunch of them, and then there's none of them. Now, obviously, this would make it so that only a few of them can possibly interact. But again, we're talking about grains of sand. We're talking about very small objects going through a very large slit. Now, the polarization of photons is very large, but the polarization is a composite feature. It's an emergent feature. It's what they look like. The little bits are tiny, okay? They're infinitesimally small things, the elements, all right? But this can be big. The space they travel in can be large. All right. So that's the first thing you got to get right, is you got to have the frequency. The frequency is everything to this story. And the truth is, you can't, you know, when the bits go in, you could have them red or whatever color. And then if you wanted to change them, the change would be is the ones that obviously are going by the surface, and what you're simulating is hitting electrons. So you're saying a certain number will hit 1 electron and move this much, and some will hit 2 electrons and move this much, and some will hit 3 electrons and move that much. So you're just talking about an angle, a spread. So, and it just comes out to be that you might as well just draw it like a light bulb or any other radiant source. And the argument would be is there's more of them that are not deflected than some are deflected, and some are deflected more, and it just goes gradually down the angle, okay, fewer and fewer as you go further off the normal. So it's less likely a photon's going to hit enough electrons to end up going at this very sharp angle, but it's not so unlikely here, 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 here. So you just make it a proportional scatter. So once you have your scatter, so now you're just, all you're doing is saying, okay, and you can't change their speed any. All right, they don't lose any speed, so they're scattering off these points. So that's what you're simulating. They haven't lost any speed, so you know, one that wasn't scattered and one that was scattered is traveling the same distance in the same amount of time. And what you're really going to just say is, where on this screen is there a hope of putting together a photon again? And so the idea that's built into the math is just an understanding that a bit from the first row, so here's the rows of photons coming in. So a bit from the first row here can go this path. And then a bit also from the first row, okay, that went by this slit, okay, but he's from the first row, but he went from this slit. And now he's going to go there also. He got scattered to that location. So one got scattered from here, from the first row. One got scattered from here, from the first row. All right? But this is a longer distance. And it's exactly a wavelength of distance. And so now it's going to remake the photon in a sense, because this one's one wavelength behind. So this one that was in the first row hits. This one that was in the first row, but it's way over here, so it's got to travel this longer distance, will hit at the right frequency here, right? And then another one from, say, this location will do the same thing, and another one from this location can do the same thing. And all those distances, if there's a full wavelength difference between those distances, it'll remake the photon. You'll end up with 4 bits with the proper distance between them. And they all came from the first row. Now there's also where they can come from equidistance, or you know, the second row, and combine with one that went the first row, because they're, say, they're in the third row, which is 3 units of time behind, and they go here, and that means the first one from the first row hit here, and then this one was actually from the 4th row. Okay, so it's, you know, and so one from here, one from the first row went the longer distance, and And then another one from the second row also went that same longer distance, and he ended up being the third photon, because he's not only in the third row, which means he's behind the ones in the front row. He went the longer distance, which added another wavelength of distance, so he's now the third. So you took one from the second row, and you took one from the first row, and they just essentially already still had the right phase. And all you did was add another one from the first row to get the 3. So you're just going based on phase, realigning the phase, getting them back in the right, getting the bullets back in the right order by combining ones that were part of a different photon. Technically, if these were the photons, you can understand that I'm taking a piece from this one, and I'm taking a piece from this one, and a piece from this one, and a piece from this one, and based on the length of these lines, I'm going to recombine them back into something in phase. And the argument is, if you do the math, that these vectors are the only vectors that'll work. That any half-length vectors are automatically out of phase. A half means you did half of this distance, or you did half distance here. A half a wavelength. And half a wavelength means you have a photon, a hit, then you have another hit too soon, then you have another hit, and then you have the right frequency. So only here do you have 500 nanometers. Here you have 250 nanometers, and 250 here, and that's not going to work. So you have to have the same distance between the bullets, restoring the same distance, and only on these vectors, only on points here where there's a wavelength of difference on the bigger line, are you going to be able to reconstruct the photon. So hopefully that's helpful in understanding there's 4 variables: the frequency of the light, the distances of the openings, or the distance between the slits more precisely, and the distance to the target. Yeah, and that's it. The wavelength dictates the phase, and they always are moving the same speed, so it's just path length. All you're measuring is how long the path is, and whether it's a wavelength of difference. Yeah, but you have to have, you have to have those variables in there, and you have to understand that it's not just about little quanta. A photon is only visible if it's quanta at a consistent frequency. Little bits at a consistent frequency. A photon happens as an event. One thing has to hit, then another thing has to hit, then another thing has to hit, and another thing has to hit. It's not just a clump. It's not just a one thing hits. That's all I can do, really, is keep trying to clarify. But obviously you can't represent a photon by a bunch of floating particles unless you understand that those floating particles, to be seen, need to hit in a sequence. Again, it's a tipping point argument. What's happening inside of atoms that makes photons visible is electrons have to be moved, and they have to be moved a specific way by specific rules. And the rule is you got to hit them before they can spring back. So you have to hit them and hit them and hit them within a certain amount of time. And that's what dictates the frequency of the light. And that's why certain frequencies are reflected and certain frequencies are passed through or absorbed by different materials, is because their electrons require a different amount of energy, so to speak, of time. They're under a different amount of pressure. Oh, that's good enough timing. So, till the next time and such.